Okay, so today we're going to finish up Chapter 6. We're going to look at the applications of exponential functions. So I mentioned at the beginning of the course when we did linear functions, if I had to pick two families of functions that are most impactful in everyday life, it's linear functions, which have a constant rate of change. Gas costs $1.95 per gallon. That's a linear function. And then exponential functions, which are a constant percentage change. We're going to talk about interest today. You have a 5% interest rate, so things grow at 5% each time. So these are the two types of things. You've got the constant rate of change, linear function, the constant relative rate of change, constant percentage change, exponential functions. So let's first just kind of review some of the basics of interest, and then we'll see how these same formulas can get used in lots of different contexts. So here's the idea behind interest. So interest is money that the bank pays you for keeping their money with the bank. So you put money in the bank, they protect it for you, and then they pay you money, right? Ostensibly because then they can use the money that they know that you've put in their bank and loan it out to other people to help other people buy things like houses and cars and things like that. And the basic calculation of interest, we let I, capital I, denote interest. R is the interest rate. And this is usually described as a percentage per year. So if we have a 5% per year, that means that R is 0.05. Okay, so there's that. P is called the principal. This is the initial amount invested. T is the number of years we're investing. And A is the amount in the account after T years. So you've likely seen this sort of thing before, but in case you haven't, or in case it's been a while, these are the variables we're working on. So some of the basic equations: the interest is the principal times the rate times the time. So example, if you invest $100 at 5% interest, for 1 year, the interest I would get would be the principal is the amount you're investing, so that's the $100. The rate is 5%, and once again, we assume these are 5% per year. So that would be as a decimal 0.05, and the time here is 1 year. So that would be, $100 times 0.5% per year times 1 year. And you see all of these units here are going to cancel out except the dollars. I get $5 in interest. Okay? Excuse me. So the amount that you would have after 1 year would be the principal plus the interest you accrued. So that would be the $100 plus the $5, which is $105. Okay? Now, at this stage, there were times when I taught this class when 5% wasn't a ridiculously high interest rate. Today, I think I checked, it's like 0.5% if you're lucky at this point. Now, if you do some algebra here, instead of going right to the numbers, if you do some algebra here, we can kind of see where the exponential factor comes into play. Because I got my principal plus my interest, I can factor the principal out, and then I multiply by 1 plus RT. And so in this particular case, I'm going to take that $100. It's going to be multiplied by 1 plus 0.05. So it's 100 times 1.05. So this is the multiplier here if we're looking at what's going on with the amount in the account. Right? So if I left it in for so let's talk about the notion of compound interest then. So let's take the same scenario. Let's say you take that initial amount, your principal is still $100. Your rate is 5% per year. And let's say you leave it in for 6 months. So 6 months, that's half a year. Then my interest would be the $100 times the 0.05 per year times the half year. And not surprisingly, you get the $5 times a half, so you get the $2.50. So hopefully that's not surprising that the amount after 6 months is $102.50. You left the investment in there for half the time, you earned half the interest back. But now if you reinvest it, so if you make this the new principal and reinvest it for the additional 6 months, so now I'm looking at 102.5 times 0.05 per year times a half a year. And you do this calculation, which we'll use Desmos to help us with. So 102.5, sounds like a radio station, times 0.05 times a half. Notice we get 2.5625. Now you're probably not going to get that. If we're looking at the amount of money, they're going to stop at 2.56. But notice then the amount that you would have at the end of the year doing this is you get an extra 6 cents. Okay? And the reason why you're getting more using this scheme than the previous scheme is because not only are you getting interest on that initial $100, you're getting interest on your interest. And that's the idea of compound interest, is you get interest on your interest. Okay? And so compounding the interest, if you stop halfway through the year, that's called semi-annual compounding. So semi-annual compounding is compounding twice a year. That means you stop halfway through the year, calculate the interest accrued, and then reinvest it as the new principal for the rest of the year. Quarterly would be every 3 months. Monthly would be every month. Daily would be like 365 times a year. So that's compound interest. Now, what you can do, and we do this in the book in detail, so if you're interested in this, I invite you. I spend a lot of time developing this formula. Is we get the formula for compound interest. A equals P times 1 plus R over N to the NT. So A, P, R, and N are the same as before. Or R and T rather, same as before. The new thing here is N. This is the number of compoundings per year. So if you don't break up the year at all, if N equals 1, then this is really simple interest. Right? So if N is 1, then you just look at what's happening at the end of each year. That's like the first case. If N equals 2, it's called semi-annual. If N equals 4, that's quarterly. If N equals 12, that's monthly. All right. Now, monthly, usually you're going to see monthly in terms of interest when it's talking about a loan to you. So if you take out a car loan or a house loan or something like that, they compound the interest monthly on the debt that you owe. And so what you can see here in terms of exponential functions, the P, that's your initial investment. That's going to be fixed. The rate and the number of compoundings is going to be fixed. So this is acting like the base of your exponential, because usually the variable here is T. And so we're looking at P times B to the NT. So the base of this exponential is a 1 plus dr over n. So let's do some examples. Once again, the derivation is in the textbook. Usually when we revisit this in calculus, I go through the derivation with the calculus students. But at college algebra, we just want to make sure you know how the formula works and to recognize it as an exponential function. Oops. So let's do an example here. So here's the formula there. So let's do an example. An account offers 5% interest compounded monthly. How much will be in the account in 30 years if $450 is invested today? Okay, so we've got our compound interest formula. A equals P times 1 plus R over N to the NT. 5% interest compounded monthly. So that tells us that the R here is 5%. And once again, that's 5% per year. As a decimal, that's 0.05. Compounded monthly means the N here is 12. How much, they're asking us how much will be in the account. So that means they're asking us to figure out what A is. In 30 years, so that's our T. If $450 is invested today, so that's our P. So A equals 450 times 1 plus 0.05 over 12 to the 12 times 30. And so once again, you see this multiplier here, 1 plus 0.05 over 12 to this power. So that's the base of the exponent, okay? So when you see this, you want to think that this is the base of your exponential function there. All right, and we're going to use Desmos for this. So once again, an exact answer is great, but if we're looking at the amount of money, we only need the answer to 2 decimal places. So let's blast over to Desmos here. And we'll type in 450 times 1 plus 0.05 over 12 to the 12 times 30. Now, in order to make sure Desmos understands what's all in the exponent, go ahead and use those parentheses there. So we're getting $2,010 and probably 48 cents. Okay, so $2,010, 48 cents. Okay. Now, if you take an economics class, another way to describe this is the future value. So, 450, not 45. So another way to say this, that the future value of $450 today in 30 years under 5% interest is roughly $2,010.48. All right. So if you hear the word future value, present value, they're working this formula one way or the other. Any questions on identifying these different parameters and then plugging them in? Whoops. All right. So the next example kind of turns it around. An account offers 2.25% interest compounded continuously. Well, we haven't talked about continuously yet, so let's actually talk about that now. So let's take a look here. So let's take a look at that last scenario. We had P was 450. N was 12, R was 0.05 per year, and T was 30 years. Okay? And so my amount here, A, was 450 times 1 plus 0.05 over 12 to the 12 times 30. Okay? All right. Now let's make this, instead of 12, let's just keep this as a variable n. All right. So I'm going to write the amount in the account as a function of n is 450 times 1 plus 0.05 over 12 to the 30n. And I'm going to see how the amount after 30 years varies by varying n. Okay? And so this is one of the ways that functions crop up in the wild all the time. You know, you've got a formula with half a dozen letters in it, and you want to look at how does the output vary by varying one of the inputs if I keep all the other ones constant. All right? If you ever take chemistry and you talk about the different gas laws, that's a perfect example of this kind of thing. So we're going to go off the Desmos here. And I'm going to write A of n is 450 times 1 plus 0.05 over n to the 30n. Okay. I'm going to make a little table here. I'll call this x1 and then A of x1 to be consistent here. And I'll just start plugging things in. So, you know, if I just compound it once a year, if I just do simple interest for 30 years, at the end of 30 years, I'd have $1,900. If I compounded it quarterly, I'd have a little bit more. If I compound it monthly, there's our answer to the problem, $2,010. If I compounded it every day, I'd have $2,016. Now, notice the more times you compound the interest, the more money you get. And hopefully that makes sense, because the more times you compound is the more opportunities to get interest on the accrued interest. Interest is constantly accruing on this money. And so by stopping more often, you're getting the interest on the accrued interest more often. So it makes sense that you're getting more. But notice the difference. Right? Going from monthly to daily, you're only getting an extra $6. Whereas going from semi-annually to quarterly, you gain an extra what? $54. And then going from quarterly to monthly, you're only making an extra $12. And so, we can think, what if you compounded it every minute? Say 365. Well, let's do every hour times 24. Or 365 times 24 times 60. So going from compounding it every day to compounding it every hour, you're only gaining 20 cents. And going from every hour to every minute, you're gaining maybe an extra penny. Okay. So what's happening here? What's happening here is something in calculus we call a tug of war. That's what I call it in calculus. It's an indeterminate form, meaning this. You are compounding more times per year. And at every instant in time, you are accruing interest. But the more times you compound the interest means the less amount of time the account has to accrue interest, right? So you have more opportunities to get interest on your interest, but it's sitting less and less amount of time between each of those compoundings. All right, so your time intervals are going to zero, even though you're compounding more. So you have this tug of war happening. And what happens is, and using calculus, they can formalize this, it levels off. Okay, so it levels off. And so we can see that. We can start plugging in outrageous numbers here. This is what I like about Desmos. Just keep putting zeros on the one. And you can see that it's leveling off. Well, now we've gotten into some round off error. So we've got to be a little careful there. But you can see it's kind of leveling off. So the question is, where does it level off to? And how can I use that then to figure out how to calculate compound interest if I compounded interest, quote unquote, continuously, meaning all the time. So we're thinking theoretically of, it's continuously being compounded. So instead of having a discrete number of times it's compounded, like 1 billion times or 1 trillion times, it's being compounded, quote, all the time. So to do that, let's take a simpler case. Let's suppose that the principal we have is $1. The interest rate is 100%. So 1. And we're going to just let the thing sit for 1 year. So our equation would be A equals P, which is 1, times 1 plus R, which is 1, over N to the N times T, which is 1. And so my A of N would be 1 plus 1 over N to the N. Okay? And so if we do that, whoops. 1 plus 1 over N to the N. Okay? And we want to look at what happens as N goes off to infinity. So we're looking at the N behavior here. I guess that's a pun. N behavior. End behavior. So as we head off to infinity, notice that this thing levels out, right? That's called a horizontal asymptote. So as n goes to infinity, a of n is approaching what number? Well, 2.718 something. And in fact, and this is where calculus comes in, you can either prove or define, depending on your point of view, that this is our number E. So that's how E gets involved with all of these things in a very natural way. So if you invest $1 at 100% interest for 1 year, and you compound continuously, you'll have E dollars. So that's how you can think about E. $1 invested at 100% interest for 1 year, compounded, quote unquote, continuously, meaning compounded all the time. At the end, you'll have E dollars. And so, and this is something we do in calculus. We can take our compound interest formula and we can let n go off to infinity, and we get a compound interest formula where the things are compounded continuously. So notice that the n's will disappear and the base of the exponential goes to E. Okay, and you can actually do some algebraic manipulation with this and do a change of variable to see if this goes to E, then 1 plus r over n to the n goes to E to the r. So 1 plus r over n to the nt goes to E to the rt. So, if you're interested in any of that, once again, you can either look in the book or ask me during office hours, and we can go through it. But, think about using this formula, the so-called PERT formula. This is sort of the most you can get out of compound interest, is if you compound the interest all the time. That's kind of the most you can get. So here, if you have an account offering 2.25% interest compounded continuously, how much should Sally invest today if she wants $5,000 in 10 years? Okay, so compounded continuously tells you we're using the PERT formula here. .25% compounded continuously, so R is 0.0225. How much should Sally invest today? So they're asking for what is the principal P if she wants $5,000 in 10 years. So that's the time, and then that's A. So 5,000 equals P, which we're trying to find, E to the negative 0.0255, whoops, not negative, times 10. All right. Now, remember, even though E is a letter, it represents a number. It's a number that's 2.718-ish, okay? This is the same E we talked about a little over, almost 2 weeks ago when we started the chapter. So I've got 5,000. I got 5,000 is equal to P times some number. So to solve for P, I would take 5,000 and divide by that number. So that's all that happens So my answer for P would be 5,000 divided by this number, e to the, and I can multiply the exponents here because I'm multiplying by 10. So all that's going to do is take 0.0255 and make that 0.255. And once again, we're going to go to Desmos to get a decimal approximation for this. So we have an answer that makes sense. So we're getting 3992.581. Was it, oh, wait a minute. Did I copy this? It's 225, excuse me. There we go. 225. And what did I dial in here? Yeah, okay. So I had it in there correctly. 3992.58. So I guess to guarantee you have the 5,000, you might want to round this up to $3,992.59. So you guarantee you have that money. Yeah, thanks, Rebecca. Thank you. Okay. Now, just like number one, if you take an economics class, they talk about the future value of money. This is the present value of money. So they're looking at $5,000 in the future. They want to know how much would that be worth today. So usually percentage rates that they're talking about in that scenario, the interest rates aren't, they're not interest rates. They're like inflation rates and things like that. Okay. So you hear this from old people like me all the time. Like, well, back in my day, I could get a Star Wars action figure for $2.99. Now you take that and go through the consumer price index and see that $3 back in 1978 is something like $15 today. All right. So future value money, present value of money, slightly different context, but it's the exact same mathematics, exact same principle. Whoops. The last thing I want to talk about here with investments is something called the doubling time. The doubling time of an investment. And I'll leave number 3 for you to do on your own. I'm going to have a different scenario because I want to show you something interesting about doubling time. So once again, the answer to these, all of these are on Blackboard. So let's talk about doubling time. So doubling time. Doubling time is a convenient way to describe how good an investment is. You can look at the interest rates all day, 5%, 7%. Well, clearly 7% is going to be better than 5%. But doubling time kind of takes it to the next level. So doubling time is how long it takes for an investment to double. So let's take our scenario. Let's say we've got the interest rate here is 5%. And let's say the interest is compounded continuously. Let's make it a little easier on us. Okay? So I know if I'm compounding continuously, I'm using the PERT formula. And they give me the rate is 0.05 t. And we want to know what's the doubling time. All right. Now, at first you might think, well, they didn't tell me how much I'm initially investing. So let's investigate this. Oh, just a second. Miss Kitty's back from her adventures today. Okay, so e to the 0.05t. All right, and we want to know what the doubling time is. So let's just say, you started off with $50. Okay? Then if I wait the doubling time, I'd be waiting until that $50 grew into what? $100. And that would be my A. So I'd have 100 is 50 times e to the 0.05t. And now we're straight back into something we did last Thursday, right? So now we're back into section 6.4. We're trying to solve something that's in the exponent. So the first step is to isolate the exponential and then take the log. So if I think about t here, t's been multiplied by 0.05. It's been put on e as an exponent, multiplied by 50. To reverse that process, I have to undo the last thing first. So I'm going to undo multiplying by 50 by dividing by 50. I've got 2 is e to the 0.05t. We're going to knock the exponential down, the exponent down using a natural log. And what's particularly nice about the natural log is that it undoes the exponent base e. And now we can divide both sides by 0.05. And once again, we're asking for the doubling time in years. If you tell somebody the doubling time is the natural log of 2 over 0.05, they'll just look at you funny. Let's go to Desmos to get a decimal approximation that'll help us out here. Natural log of 2 divided by 0.05. Roughly 13.86. Oops. So roughly 13.86, and these are years. Okay? So the doubling time to go from $50 to $100 would be roughly 13.86. All right. Now, let's see if we started off with a different starting value. Let's say you don't have $50 to invest. Let's say you've got $1 to invest. Or let's make it kooky. All right, let's make it like $1.42. Then after the doubling time, we're looking to see how long it gets to $2.84. So you'd have $2.84 is equal to $1.42 times e to the 0.05t. And then you would divide both sides by $1.42. And lo and behold, 2.84 divided by 1.42 is what, folks? It's 2 again. Okay? So the doubling time doesn't depend on the initial amount. It's going to be roughly 13.86 years either way. Okay? We can prove that. If we wanted to prove it in general, if I start with the value p and we go to 2 times p would be the doubling time. That would be our value for A. So 2p would be p times e to the 0.225, back in the last example, 0.05t. Whatever the p is, you would divide both sides by p. 2 is e to the 0.05t. Take the natural log of both sides. And we're literally back to where we started here. Okay? And we can even do one better, because let's say you had interest rate R here, interest rate. So if we just had interest rate R here, R here, R here, you'd have the R here, and we have that the doubling time is the natural log of 2 over R. That's if the interest is compounded continuously. So, the moral of the story here is, because compound interest is exponential growth, it's a constant percentage growth. So it doesn't matter what you start with. You're growing at the same percentage regardless of what you start with. So to get up to 200% of where you started, it's going to be the same time regardless of what you invest. Okay? And that's a pretty powerful idea. That's a pretty powerful idea. So here you're basically comparing doubling times if you compound the interest monthly versus compounding the interest continuously. Now, what would you expect? The more times you compound, the faster you should get to that 200%. So if you think about your investments, the shorter the doubling time, the better, right? The shorter the doubling time is, the faster you get more money. Okay. So that's compound interest. Compounded a finite many times a year, N, versus compounded all the time. And this formula, the PERT formula here, can be picked up and used in a couple more interesting contexts. So if you look at the graph of this thing, so thinking A as a function of time, A of t is PE to the RT. So when we write the A of t here, since there's so many letters, we're just specifying here that the T is what's changing. The P and the R are constant. You know, if we're in an interest scenario, we're in an investment scenario, then the R is positive. The graph is going to look like, starts here at the initial principal P, and then it's just going to grow exponentially. Okay? And so this is classic growth curve. This same phenomenon, this is called unlimited or uninhibited growth. Basically, the underlying principle here is the more you have, the faster it grows. Now, hopefully that makes sense because we're looking at a percentage growth here. So the more you have, the faster it grows. That's the underlying principle here. All right? If you have $1,000 that you start with, then at the end of 1 year, you're going to have more interest than if you started with $1. You'll have the same percentage growth, but you're going to have a faster growth. Okay? So that same principle can be applied to, for example, bacteria in a petri dish. If you have a petri dish and you inoculate it with some bacteria, the bacteria have all the food, all the room, and they just will take off and they will grow exponentially according to the same type of curve. So you might see the PERT formula in biology. You might see the PERT formula written like this. Where N naught is the initial population and the K is the growth rate. And so you can talk about the doubling time of the bacteria or the yeast. And so in the homework, there's a couple questions like that. When you see the law of unlimited or uninhibited growth, basically it's the PERT formula. Instead of initial investment P, you've got the initial population. And instead of the initial growth rate, you've got that. Okay? Now, you can kind of turn this around. And instead of having a growth curve, you could have a decay curve. So A of t equals A naught e to the kt. If your k here is negative, then we start at a certain amount A naught and we decay. We saw an example of this on the very first day we talked about chapter 6. So almost 2 weeks ago, we saw depreciation. We saw depreciation. All right. And so depreciation, we had our value of the car. I forget what it was. I'm going to say it was like 7,000 times 0.8 to the t. Well, you could rewrite this using change of base to e to the t times the natural log of 0.8. And if you calculate the natural log of 0.8, since it's less than 1, it's a negative number. So let's draw that up on Desmos. Negative 0.22, etc. So the value could be rewritten using the change of base as 7,000 e to the minus 0.22, etc. times t. And so that means we have a decay curve or depreciation curve. Okay. Now, another main application of decay curves besides depreciation is radioactive decay. So there are atoms that are unstable, and what the atoms do is they literally turn mass into energy, and so they literally disappear, and their mass, the matter decays and turns into radiation. Okay, so radioactivity is the Einstein mass E equals mc squared mass energy conversion. That's mass energy conversion right there. Okay. Now, radioactive decay is used for all kinds of things. It's used to try to figure out the age of artifacts by looking at the ratio of radioactive carbon to the isotopes there left over. It's used in treatments, radiation treatments in the hospital. It's also used to try to sterilize produce. It's used in smoke detectors. So radioactive decay, and of course down the road there at Perry Nuclear Power Plant, right? It's radioactive decay, nuclear fission there. All right. So our next example has to do with radioactive decay. So let's take a look at that. So it says aluminum Fosdax, the shaving cream atom, decays according to the formula A of t equals A naught e to the kt. So once again, this is a version of PERT. The A naught here is like the P here. P was the initial investment. A naught here is the initial amount of radioactive material. R is the growth rate. Here K would be the decay rate. So we assume that the K should work out to be a negative number. Aluminum Fosdax, that's my spelling of the element from the original Duck Dodgers cartoon. So you can YouTube that. The original Duck Dodgers, they were looking at that. And it was the shaving cream atom. So if the half-life of this element is 25 minutes, find and interpret the decay constant K. So here they're talking about half-life. So in the previous example, we looked at doubling time. Doubling time was the amount of time it takes for the investment to double. That's if you're in a growth scenario. Here we're in a decay scenario. So as time goes on, we're getting less and less of that material. And so at some point, we're going to get down to half of what it originally was, and that's half-life. So the half-life is 25 minutes. Find and interpret the decay constant K. All right. So once again, just like doubling time, half-life does not depend upon the initial amount. And we're about to show that here. If I start off with my initial amount, A sub 0, and I let a half-life go by, whoops, then I would be back to 1/2 what I started. And so this would be my A. So 1/2 A naught would be A naught E to the K times T, which they're giving us here is 25 minutes. And so just like before with doubling time, it doesn't matter what the A naught is because it's going to get divided out. And now to get the K out of the exponent, I'm going to take the natural log, as we are wont to do. And I'm going to write this as 25K now because we know that 25 is in minutes. The natural log and the exponential function base e completely undo each other because they're inverses. And so I'm going to be left with just a 25K. And then divide by the 25. So I get the natural log of 1/2 over 25. And once again, in this applied situation, that's really not telling us much. So let's get a decimal approximation. Now we know that 1/2 is less than 1. So we know the natural log of that is going to be negative, which is good. But let's see what it works out to be. Natural log of 1/2 divided by 25. Make sure you're dividing that 25 outside the natural log. You see how that's positioned there? And we get negative 0.277, etc. Okay? And so to interpret that, well, the negative means that it's decay. And 0.0277, that's roughly 2.77%. So the decay rate is roughly 2.77%. Okay? So the negative tells us it's decay and not growth, and the rate is about 2.77%. Any questions on finding the decay rate given the the half-life? So in the previous example, we knew the rate to get to the doubling time. Here, we're given the half-life to get to the decay rate. So it's the same mathematics. And that's what I want you to focus on in this is the same mathematics that we learned on Thursday are being used in all kinds of different applications here. And then let's look at part B. How long does it take for 90% of this material to decay? Okay, so how long does it take? So 90% to decay means we're going to start off with some amount, A naught, and 90% decays. How do I calculate how much is left? Well, if 90% decays, then that means there's only 10% left. And so it would be 0.1 times A naught. For example, if we had 100 to start and 90% decayed, then I'd be left with 10. 100 grams, whatever. Does that make sense or not? So I go to my formula. A equals A naught e to the kt. The A is 0.1 A naught is equal to A naught e to the minus 0.0277-ish t. Once again, what the A naught is doesn't matter. It's going to cancel out. Take the natural log of both sides. The natural log and natural log and the exponent base e are inverses. They completely undo each other. So then t would be the natural log of 0.1 over negative 0.0277. This looks like, at first glance, you're going to end up with a negative number, which doesn't make any sense. But remember, what I'm plugging into the natural log there is less than 1. So the natural log of 0.1 itself will be negative. And so I'm taking a negative divided by a negative. So it will be a positive, and let's see what it's going to be. Guess I don't need this anymore. The natural log is 0.1 divided by negative 0.0277. And in fact, if we wanted a more exact answer, we can put this whole thing. So using 3 decimal places, there are 4 decimal places, I'm getting 83.12. We can just copy and paste this whole thing in down there if we want to get a 83.04. So we're looking at roughly 83 minutes either way. All right. And I suppose I should say this decay rate is per minute. All right, it's per minute because we're measuring t here is measured in minutes. All right. Now let's see if that makes sense. Let's see if that makes sense. We know what the half-life is. The half-life is 25 minutes. The half-life is 25 minutes. So if I start off with an initial amount, after 25 minutes, I'm going to get to half that amount. And after another 25 minutes, I'm going to get to half of that amount. So half of the half. So I guess I'll write this as a half. Well, yeah, I'll do both. So that's 0.5. And then here I would get to half of the initial amount, which would be 0.25. And then after another 25 minutes, I would get half of the half of the half of the initial amount, which would be 0.125. So every 25 minutes, I'm down to half of what I started. So after 25, 25, 25, so after 75 minutes, I'm down to 1/2 cubed, or 1/8 of my initial amount. Now, to get to 10% remaining of my initial amount, we got roughly 83 minutes. So you see how that makes sense? I mean, it's got to be more than 75, but less than 100. Because if you go to 100, then I'm taking half of that again, and that's going to be under 0.1. Okay. So just like doubling times can give you a rough estimate of how long it's going to take to increase, half-life can be used the same way to guesstimate how long it's going to take for a certain amount to decrease. Okay, so there's that. All right, so the PERT formula and its different manifestations in different fields is one model for growth and decay. And once again, it's an unlimited or uninhibited model, meaning that, you can just, if it's a growth model, everything just heads up to infinity. If it's a decay model, everything's going to head to 0. There's no floor or ceiling with those types of things. Number 5 introduces us to a type of limited growth model, Newton's law of cooling. Whereas in the unlimited scenarios, the amount you have is proportional, or excuse me, the rate of increase or decrease is directly proportional to how much you have. So the more bacteria there are, the faster they grow. The more material you start with, the faster it decays. Newton's law of cooling puts some kind of condition, some kind of limit. So for example, if you take a frozen pizza out of the freezer and let it sit on the table, it's going to warm up. Okay? But unless you put it in the oven, it's not going to warm up to anything higher than room temperature. Okay? So room temperature, that's this T sub A here, is the ambient temperature. That's the temperature of the surroundings. If you take a piping hot cup of coffee and sit it on the table, it's going to start to cool off, but it's not going to get any colder than room temperature unless you put it in the fridge or something. So Newton's law of cooling is an example of what's called a limited growth or decay. And Newton's law of cooling says, or warming says, the rate of warming or cooling is directly proportional to how much room there is to cool or to warm up. All right? So the colder something is, the faster it's initially going to start to warm up. And then as it gets closer to room temperature, it's not going to be warming up as fast. That hot coffee, when you set it on the table there, initially that hot coffee is going to cool quickly until it, but the colder it gets, right, it's not going to be cooling as fast. Okay? So TA here is the ambient temperatures, temperature surroundings. T naught is the initial temperature of the object. Okay. So suppose a piping hot cup of coffee at 180 degrees Fahrenheit is served in a room that's 72 degrees Fahrenheit. After 10 minutes, the coffee is 155 degrees Fahrenheit. So assuming that the coffee cools according to Newton's law of cooling, find a formula for the temperature of the coffee T of T as a function of the number of minutes it has been left to cool, T. So T of T equals T sub A. That's our ambient temperature, which is 72 degrees Fahrenheit. So I'm going to write 72 there, plus T naught minus TA. T naught's the initial temp of the coffee, which is 180 degrees, minus then 72 degrees, e to the minus kt. And so here's what we know about the model so far. It's 72 plus 180 minus 72 is what? 108 e to the minus kt. Now, in order to get temperature as a function of time, I got to figure out what the K is. I don't know what the K is yet, but they give us a piece of information to use. After 10 minutes, the coffee is 155 degrees Fahrenheit. So using functional notation, this tells us that capital T of 10 is 155. The input here is time. The output here is temperature of the coffee. So using that, T of 10 is 155. I can take this expression and plug in 10. And get my equation, 155. So let's take a minute to make sure we're all good with where that equation comes from. So once again, now we're back into what we did on Thursday. So 72 plus 108 e to the minus k e to the minus 10k is 155. So I'm going to subtract 72 from both sides. So I got 155 minus 72. Was that 83? Divide both sides by the 108. Take the natural log of both sides. The natural log and the exponent base log undo each other, or exponent base e rather, undo each other. So k is the natural log, 83 over 108, divided by negative 10. And once again, we're heading off to Desmos here to get a decimal approximation. So you can see here it's the same process we did last Thursday. Isolate the exponential. And then we take natural logs. So natural log of 83 over 108 divided by negative 10 is 0.0263. Okay. And so putting that back into the model, T of t is 72 plus 108 e to the minus kt. So the k here is positive, so e to the minus kt would be e to the minus 0.0263 t. So that would be our model. Okay. So what does it ask us to do? How long does it take for the coffee to cool to 120 degrees? Find and interpret the horizontal asymptote. Okay, so here we go. How long does it take to cool to 120 degrees? So we're asked to find how long does it take to cool to 120 degrees. Now, based on the information they gave us, if it takes 10 minutes to get to 155 degrees, it should take us longer than 10 minutes to get to 120 degrees. So let's figure that out here. So we want to figure out how long, little t, it takes for the temperature, big T, to get to 120. And hopefully you see that we're solving the same type of equation we just did to solve for k. We're going to subtract the 72 from both sides. And what's 120 minus 72? $48. Divide both sides by the 108. E to the minus 0.0263t is 48 over 108. So once again, we've isolated the exponential. And we're going to take logs. So take the log of both sides. I'll pick this up on the next page. Remember that the natural log and the exponential base e completely undo each other because they're inverses. And now we divide both sides. So t is the natural log of 48 over 108 divided by negative 0.0263. And remember, t is supposed to be the amount of time it takes for the coffee to cool to 120 degrees. It started at 180 degrees. The room temperature is 72 degrees. So at some point it should get to be 120 degrees. You might be a little alarmed because we got that negative there, but don't panic because look at what's going on inside the natural log. Inside the natural log, we have a number less than 1, and we know that the log of that's going to be negative. So let's actually get a calculation here. And 0.0263. So we're getting roughly what? 31 minutes? So notice after 10 minutes, it went from 180 to 155 after only 10 minutes. To go from 155 to 120, it's taking like an extra 20 minutes to do that. So once again, the colder it gets, the cooling rate is less. Okay, so the cooling rate isn't... it's not cooling as fast as it did initially because we're getting closer. So let's look at that horizontal asymptote question. So to get to the horizontal asymptote, let's look at our original function here. 72 plus 108 e to the negative 0.0263 t. So let's dial it into Desmos. And we'll look at the horizontal asymptote three ways. All right, so what are the three ways we look at the horizontal asymptote? Well, the first way is we'll just think about what it should be. Remember, how do we get horizontal asymptotes? Horizontal asymptotes come from end behavior. So in this particular case, the only end behavior that makes sense is letting t run off to infinity, because you can't go back in time before the coffee was served. So as time goes by, what should the temperature of this coffee reach? Well, it should be 72 degrees Fahrenheit. It should be the room temperature. You follow? So that's one way we're going to look at the horizontal asymptote. Another way we can look at the horizontal asymptote is graphically, or numerically. So let's start off with looking at x equals 1. And, oh, it's upset at me. There we go. And let's just start plugging in bigger numbers. And as time goes by, well, of course, it's telling us 72 exactly, but it's actually a little bit more than 72. You can see that the function values level off at 72. And we can test that graphically looking at y equals 72. and making that a dashed line, as is our custom here. And of course we don't see anything because our window isn't correct. So for the X, we'll go from, I don't know, 0 to 100. And for the Y, let's go from 0 to 100. And there we go. Excuse me. The coffee there initially. There's the coffee initially there at 180 degrees. You can see it starts to cool off. And if I kind of zoom in here at the slope, as we go further down, notice the slope gets less steep, right? It gets less steep. So as time goes by, it's still cooling, but not cooling as quickly. Now, you might ask, based on this model, you might ask, does the temperature ever actually reach 72? In other words, does the graph cross the horizontal asymptote? Because we saw in chapter 3 that sometimes that can happen. Well, let's see that. So that's sort of a follow-up question. Can the temperature ever equal exactly 72? Well, we can look at this algebraically. Now, when you go to isolate the exponential and subtract the 72 off both sides, look what happens. Now we know that 108 is positive, so I could divide that out. Now I've got e to some power equals 0, and there's no real number to do that. You actually explained that on the last take-home. You can't take e to a power and get 0 because e is a positive number. A positive number to any power is going to be a positive number. So this model says that you never actually get to room temperature. You just get closer and closer to room temperature. Okay. So it's a limitation of the model. Okay. Any questions on that? So hopefully you can see in chapter 6 how a lot of the concepts we've been working on since chapter 1 are coming into play here. Right? On this problem alone, we've got, we got all the algebra we could want, solving these different equations. We're solving for different parameters of the model. We're looking at things algebraically. We're looking at things numerically. We're looking at things graphically. Okay? So all the big ideas are kind of coming together here in chapter 6. Okay. So the last problem we're going to work on today is an example of what's called a logistic curve. So unlimited growth, think of bacteria in the petri dish, think of money in an investment account. There's no limit to what you can get. Right? The growth rate is directly proportional to how much is there. Newton's law of cooling or warming. The growth rate is directly proportional to how much room there is left to grow. So you take that cold pizza out of the freezer. Initially, it's going to warm up quickly, but then it's still going to be warming up to room temperature, but it won't be warming up as quickly. The logistic idea combines both limited and unlimited growth. So it says that the growth rate is directly proportional to not only how much is there at the time, but how much room there is left to grow. So you have a limiting amount. Okay. So early on, the growth looks exponential, and then it tapers off to be more of a limited exponential. So let's actually dial this into Desmos here and see this graph. So we got our P of t is 150 over 2 plus 73 e to the negative 0.5 t. Let's take a look at what's going on here. All right. Oops, let's zoom in a little bit. Okay. So this is a classic exponential or a classic logistic growth. If you notice initially, you're down here, we got 0, comma 2. That means if you plug in 0, you get out 2. That means initially there are 2 Sasquatch on Roscus Acres in the year 2003. Okay? And now the population starts to grow. Now if you look early on, that looks like dead on exponential growth. That looks like the growth curve you would expect for exponential growth. But then at some point, look what happens. At some point, you see what happens? It's still growing, but not as much. Now, the point where that happens is called an inflection point. The point where it goes from unlimited growth to limited growth is called the inflection point. In this particular example, the inflection point happens at, oops, not 75. Let's see. 75 over 2, right? 75 over 2. Yeah, 37.5. Now, this is something that you can use calculus to show. You can show that, you've got your limiting amount here, which is 150. Or excuse me, 75. I keep getting that. I keep getting ahead of myself there. So the limiting amount here is 75. And that's something we can show using the old numerical trick. Just start plugging in bigger values there. Okay, so this means that 75 is what they would call the carrying capacity of Sasquatch and Roscus Acres. As time goes by, your population can go no further than 75 Sasquatch. So it turns out, and once again, you would need calculus to show this. If you take your limiting amount and cut that in half, that's when the growth changes from exponential unlimited growth to limited exponential growth. And you can see that right there. You've got that rapid growth, characteristic of unlimited growth, and then here it changes to limited growth. Okay? So that's logistic. You can see it there graphically. So let's get into the problem here and see what it asks us to do. Find and interpret P of 0. Well, we kind of already spoiled that one looking at the graph, but let's go ahead and do the algebra here. So remember, P at 0 means everywhere you see a little t, we're going to plug in a 0. So that's 150 over 2 plus. Now, 0 times negative 0.5 is 0. E to the 0, remember, is 1. E to the 0 is 1. So I've got a 73 down there. So 150 over 75 is 2. So that's the find part. Now the interpret part means to tell me what that means in terms of time and Sasquatch. So P of 0, that means we're 0 years after 2003. So that means in the year 2003, there are 2 Sasquatch. Okay, so that's the initial population of Sasquatch. What is the population in 2007? Well, in 2007, that's 4 years after 2003. So you would take P of 4, and you would plug in 4. And once again, we would likely get a crazy decimal for this. So let's look at Desmos to see what P of 4 is. We're getting 12.62. And so how would we record that? Well, P of 4 is 12.62, etc. So in 2007, there are between 12 and 13 Sasquatch. Okay. Any questions on what the inputs mean here and what the outputs mean? That's really what parts A and B are getting at. Whoops. Solve P of t equals 50 and interpret. Okay, so let's do that on another page here. Solve P of t equals 50. So P of t is 150 over 2 plus 73 e to the negative 0.5t. And that's 50. So this is like one of those equations we had back on Thursday. We've got the t that's in the exponent. It's being multiplied by negative 0.5. Put on e as an exponent, multiply by 73, adding 2 to it, and dividing it into 150. So to isolate the exponential, we got to first chase it out of the denominator. So we can do that by multiplying both sides by the 2 plus 73 e to the minus 0.5t, or you could do the cross multiplication thing that all the cool kids are doing these days. Like that. And then we can distribute. Now what's 50 times 73? So let's just do 5. 5 times 70 is 350. And 15. So that's 365. So 3650. E to the minus 0.5t. Let's double check that. Excuse me. So 5 times 70 is 350. 5 times 3 is 15. And multiply by 10. So then we're going to subtract off the 100 from both sides. And divide by the 3650. So that's 5 over 365. That's going to be 1 over what? 73 again? So I can take the natural log, cancel out the e, so negative 0.5t is the natural log of 1 over 73. So t is the natural log of 1 over 73 divided by negative 0.5. And once again, don't worry, because what's inside the natural log there is negative. So negative divided by a negative is going to be a positive. So we will get a meaningful answer here. Let's go to Desmos to approximate that. So I need the natural log of 1 over 73 divided by negative 0.5. That's roughly 8.58. Okay. So that's the solve part. Okay. And once again, we can check this graphically. We've got the graph up there. Let's look at y equals 50 and see where that crosses. If I click, boom. There's my answer, 8.58, etc. You follow? So might as well check it graphically there. Now, once again, what does that mean? So what's the interpretation here? So what's the interpretation there? So after approximately 8.5 years, the Sasquatch population has grown to 50. All right. Now, after 8.5 years, so you could add that, to your original 2003. So you can say between 2011 and 2012, your population's up to 50. Okay. Find and interpret the horizontal asymptote of the graph. Well, we did that already. Okay, we did that already. We got the horizontal asymptote, looking at it numerically there, y equals 75. So that means as time goes by, the Sasquatch population will grow to 75. So once again, since that's sort of the limit of the population, you may hear this called the carrying capacity of the environment. Okay? All right, so that's exponential growth and decay. There's things out in the media now that talk about exponential growth and decay, but those kind of topics can be troublesome for people, so I kind of shied away from some things. But you just Google search exponential growth in the news, and you're going to see that certain things in the wild now are following these very closely, these types of exponential growths. Okay. All right, folks, that'll do it for Chapter 6. Let's take a look at the take-home. We got the take-home due this week, which I think we talked about already. Let's take a look at the take-home due tomorrow, and then the take-home due on next week. We're looking at take-home 10, take-home 11. Let's take a look at these. So take-home 10, yeah, we did look at this, I think, last week. So this is going back to last Tuesday, a week ago, properties of logs. This is section 6.3, both number 1 and number 2. All right. Remember on number 2, you want to use your inverse property to rewrite 1 as a natural log. So we did an example like that last Tuesday. There's some in the homework there. And then number 2 is we're solving a variety of exponential. So we got a couple exponential equations to solve and a log equation to solve. Okay. So this is like what we did last Thursday. So A and B are from section 6.4. C is from section 6.5. Assignment 11. This is a callback to the very first thing we did in section 6.1. So now that you've had more time to work with these functions, so this actually goes back, if you look at the lecture, it goes back to section 6.1. We talked about this. And then here's the concept of half-life. So here's half-life in a depreciation scenario. And then number 2 and 3, that's the kind of nonsense we're going to be working on Thursday. So if you've already finished Take Home 10, then you can start working on Take Home 11 here. Okay? Alrighty, folks, as always, I appreciate you tuning in. I hope you have a great rest of your day. We're supposed to get up into the 60s tomorrow. So I hope you get a chance to get out and enjoy the temperature and the sunshine before it's gone for a few months.